Hello everyone, my name is RLibm and I'm a PhD student in Rutgers University with my advisor Santosh Nagarakate. It looks like recently a lot of new number representations for approximating real numbers are being proposed. I'm not saying it's a bad thing, but it means that we should have math libraries for these new representations. So today I'm going to present a novel approach to generate correct and fast math libraries for these representations. In the last few years, we saw a number of new representations for approximating real numbers being proposed. Professor John Gustafson proposed the posit representation, which provides tapered accuracy. Google and Intel proposed bfloat16, which is a 16-bit floating point representation with 8 bits for exponent. Microsoft proposed MSFP, which is a floating point configuration with 8 to 11 bits. And NVIDIA proposed TensorFloat32, which is a 19-bit floating point representation with 8 bits for exponent. These representations are proposed for the applications in neural network and high-performance computing to provide high throughput as well as sufficient amount of accuracy in the results. As such, these communities are very excited about the new representations. But to effectively use the new number systems, especially in the domain of machine learning and high-performance computing, we need math libraries for them. However, because these representations are so new, there are currently no math libraries for them. Since these representations will be primarily used in numerical applications, it would be really great to have native math libraries for each of these new representations. Now, there are two important requirements for math libraries. First, math libraries should be correct. If the math library itself produces incorrect results, then there is no hope for applications using it to produce the correct result, even if the rest of the application is numerically correct. Second, math libraries should be efficient. A slow math library will significantly slow down the application that uses the math library. Then the developers will choose not to use the math library even if it produces correct results, and search for a more efficient math library at the cost of producing erroneous results. So in this presentation, I would like to share with you our new results in developing correct and efficient math libraries, the challenges in creating them, and our solution to tackle this problem. We present a novel approach to create math libraries that are both accurate and fast, and our approach can automatically generate approximation functions using linear programming solvers. Using our techniques, we created RLibm, a math library generator, and fast and correct math libraries for bfloat16, posit16, and float representation. So let me first start off by talking about what it means for a math library to be correct. To illustrate, here's a number line in real numbers. Fixed precision representation like floating point representations can only represent finite number of rational numbers exactly. So you can't exactly represent irrational values like natural log of x1 here with these representations, and you have to round these kinds of values to a representable value using a desired rounding mode. In this talk, we will use the round to the nearest, tie goes to even rounding mode. So natural log of x1 rounds to the value v1. If our natural log of x math library function produces v1 for the input x1, then we say that it produces the correctly rounded result for the input x1. If our natural log of x function produces any other values, like v2 or v3, then we say that it does not produce the correctly rounded result. If natural log of x function produces the correctly rounded results for all possible inputs, then we say that the natural log of x function is a correctly rounded function. If all approximation functions in a math library are correctly rounded math functions, then we say that the math library is a correctly rounded math library, or correct math library for short. But in the past, creating correctly rounded math library has always been a difficult task, and let me show you why by first telling you how a math library function was usually constructed in the past. In a high level, the most widely used method to create an approximation function for an elementary function f of x was to mathematically derive a polynomial approximation of f of x, something like this. And the most common method of generating a polynomial approximation is to use a minimax approximation method. The goal of minimax approximation method is to identify a polynomial that minimizes the maximum error of the polynomial compared to the real function f of x. Currently, the state-of-the-art algorithm for minimax approximation is the Remez algorithm or its variants. And to increase the accuracy of the result, the polynomial approximation is evaluated in a higher precision representation compared to the target representation of the math library. For example, if we want to create a math library for a 16-bit representation, we might evaluate the polynomial using the 64-bit double type. However, polynomial approximation alone is not sufficient to produce accurate results for all inputs. As you can see from this graph, polynomial approximations can approximate a small region of inputs with relatively high accuracy. But outside of this small region, the error increases significantly. So math library functions typically utilize what is known as range reduction to transform any arbitrary input to a value in this small region to increase the accuracy of the polynomial approximation. Let me show you an example of range reduction using natural log of x. When we are given an input x, we can break the input down to x prime times 2 to the power of m, where x prime represents the significand of the input and m represents the exponent of the input. Then we can compute natural log of x with natural log of x prime times 2 to the power of m. Next, we can use mathematical identities of logarithm functions to break this formula down to natural log of x prime plus natural log of 2 to the power of m, and further break it down into natural log of x prime plus m times natural log of 2. Notice that m is an integer value that can be extracted from the input x, and natural log of 2 is a constant. So we can approximate natural log of x by just approximating natural log of x prime and adding the value m times natural log of 2. Additionally, the values of x prime are always in the range of 1 to 2. This means that our polynomial approximation of natural log of x prime needs to accurately approximate natural log of x for inputs between 1 and 2, but does not have to be accurate for other inputs. Now let me do a recap and go through how a math library implementation of natural log of x might look like. First, when a math library function is given an input x, we convert the input to a higher precision representation h. Next, math library performs range reduction on x and extracts x prime, which is in a smaller domain. Third, the reduced input x prime is used with the polynomial approximation function generated with minimax approach to produce a value y prime. Now y prime is an approximation of natural log of x prime, not natural log of x. So math libraries compensate the output by using the formula y equals y prime plus m times natural log of 2 to compute an approximation of natural log of x. Finally, the result y is rounded to t and returned. Now, by simply looking at this process, it looks like it's not too difficult to create correctly rounded math libraries. Mathematically, everything checks out. Range reduction and output compensation functions are mathematically correct, and there are numerous methods to generate accurate polynomial approximations for a small range of inputs. However, our problem is that these techniques are based on mathematics in the world of real numbers. Our goal is to generate approximation functions for finite precision representations, and this creates a set of challenges. For example, let's go back to our real number line. The blue circle, which is the real result of natural log of x1, is located relatively close to the midpoint between v1 and v2, the two closest representable values in our number representation. Since v1 is the correctly rounded result, our approximation function has to produce a value in this gray region in order for the result to round to v1. Otherwise, it will round to a wrong value. But since math libraries produce polynomial approximations that approximates the real value of natural log of x1, in reality there is only this much room for error. This means that our polynomial approximation has to be extremely accurate. But let us suppose that we do generate accurate enough approximation mathematically. Well, we have to evaluate p of x in a fixed precision representation, so there is bound to be numerical error. On top of that, the output compensation function also has numerical error. And at the end, we end up with enough error so that our approximation function produces wrongly rounded result. So are we doomed? Well, not exactly. Remember what our goal was. Our natural log of x function produces correctly rounded result for input x1 if it produces v1. The goal of natural log of x math library function is not to compute the real value of natural log of x1. So instead of trying to approximate natural log of x1, we should try to approximate v1. Then our approximation can produce any value within this gray region, whether it would be this value, this value, this value, or this value. Our result will round to the correctly rounded value v1. And this is the key insight in our approach. Our key technique is to identify what the gray areas should be, and then use LP solver to automatically generate the coefficients of the polynomial that produces a value in the gray region. Additionally, to account for the numerical error in range reduction and output compensation formula, we're going to adjust this gray interval such that if the polynomial produces a value in this reduced interval, then the result of the output compensation formula rounds to the correctly rounded result. So now let me illustrate our approach in high level using a specific example. We're going to create an approximation of natural log of x for 5-bit floating point representation with 2 exponent bits and 2 mantissa bits. Our 5-bit floating point representation can exactly represent 23 real values ranging from -3.5 to 3.5. We're going to use a double type for our internal computation to evaluate the polynomial approximation, range reduction, and output compensation. The first thing we're going to do is we're going to identify special case inputs. The elementary function natural log of x is defined for inputs from 0 to infinity, not inclusive, so all inputs not in these range are considered as special cases. If an input is special case input, then we simply return what the result is supposed to be. Once the special case inputs are removed, then we're left with 11 inputs ranging from 0.25 to 3.5. So our next second step is to use an oracle that can compute the real value of natural log of x and compute the correctly rounded result for each of our 11 inputs. This step tells us what the final rounded result should be for each of the possible inputs. Next, based on the correctly rounded result, we identify what the values of our internal computation should produce. Our internal computation is evaluated in a higher precision representation, double. So there are a range of values that our internal computation can produce and still round to the correctly rounded results when we round it back to 5-bit floating point. We call this range of values the rounding interval. Now our goal is to come up with an internal computation that produces a value in the rounding interval, which I show using the gray area in this graph. At this point, if we do not intend to use range reduction, we can jump to the last step where we generate a polynomial that produces a value in the rounding interval. However, in most cases, we need to use range reduction to reduce the range of inputs that we need to approximate. Remember that when range reduction is involved, the original input x is transformed into the reduced input x prime using the range reduction function. Then we use the polynomial approximation function to approximate the value of natural log of x prime to produce the reduced output y prime, which is used with the output compensation function to compute y, the approximation of natural log of x for the original input x. Also, to produce the correctly rounded result, the output y should be within the rounding interval that we computed in the previous step. So to generate a polynomial approximation of natural log of x prime, we want to identify what the inputs and outputs of the approximation function of natural log of x prime should be. In our case, they're the reduced inputs x prime and the reduced outputs y prime. Therefore, in our fourth step, we compute the reduced inputs and the range of values that the reduced output y prime can be for each input x. To compute the reduced input, we use the list of inputs x and perform range reduction on them to produce the reduced inputs x prime. The graph shows the reduced inputs in the x-axis below each of the original inputs. Next, we identify what the range of values that y prime can be. Y prime should be a value such that if we use the output compensation function with it, the result is in the rounding interval. Therefore, we use the rounding interval and reverse engineer the output compensation formula to identify a range of values for y prime. We call this range of values the reduced interval. Our method computes the reduced interval such that if our approximation of natural log of x prime produces a value in this reduced interval, then it is guaranteed that the output compensation function will produce a value in the rounding interval. This means that our process also has to take into account of any numerical errors that occurs while evaluating the range reduction and the output compensation function. The graph now shows the reduced interval for each original input x. To learn more about the specific techniques that we use to compute the reduced input and the reduced interval, please read our paper. Now at this point, you may have realized that there are several inputs x that are mapped to the same reduced input x prime. For example, there are 4 inputs 0.25, 0.5, 1.0, and 2.0 that all map to the same reduced input 1.0. However, the reduced interval for each inputs are all different. This is because of the numerical errors of floating point representation and the fact that our reduced intervals take into account of these errors. Each reduced input tells us what p of x prime should produce in order to approximate natural log of x accurately. For example, the reduced interval corresponding to x equals 0.25 tells us that p of 1.0 should produce a value in this region to produce the correctly rounded result of natural log of 0.25. The reduced interval for x equals 0.5 tells us that p of 1.0 should produce a value in this region for us to correctly approximate natural log of 0.5, and so on and so forth. In other words, our polynomial approximation, p of 1.0, must produce a value in all 4 of the reduced intervals for our natural log of x to produce the correctly rounded results for the inputs 0.25, 0.5, 1.0, and 2.0. Therefore, if there are any reduced intervals that correspond to the same reduced input, we merge the intervals by computing the common region. In our graph, we show the reduced intervals corresponding to the same reduced inputs with the same color, and highlight the common region with darker shade of the color. Once we merge the reduced intervals, we're left with 4 reduced intervals, with reduced inputs ranging from 1.0 to 1.75. These reduced inputs and intervals tells us what the inputs and the outputs to our polynomial approximation has to be. So our final step is to generate a polynomial approximation p of x using these 4 input-output constraints. In fact, if you take a closer look at these constraints, they are linear constraints for solving for the coefficients of the polynomials. So we can encode this constraint into a system of linear inequalities that solve for the coefficients. In our example, we created a system of linear inequalities that solve for the coefficients of a monomial that satisfies all 4 constraints. Then we can give this system to an LP solver to generate a polynomial that satisfies all 4 constraints. This polynomial, used with our range reduction and output compensation function, produces the correctly rounded result of natural log of x for all x in our 5-bit floating point representation. Finally, let me show you how we can implement the natural log of x function. First, we determine if an input is a special case input. If it is, we return the correct result accordingly. Next, we round the input x to double and compute the reduced input x prime based on our range reduction function. Then we evaluate our polynomial approximation with the reduced input x prime, which approximates natural log of x prime, and perform output compensation function to produce an approximation of natural log of x. Finally, we round y, our approximation of natural log of x, back to our 5-bit floating point representation and return the result. Using this approach, we created the RLibm, a collection of math libraries that provide several math library functions for bfloat16, posit16, and 32-bit float representations. We used MPFR math library with 2000 precision bits for the oracle to compute the correctly rounded result. All of our experimental evaluations were performed in a machine with 4.2 GHz CPU running Ubuntu 16.04. In our experiments, we wanted to check for 2 things. First, does RLibm produce correctly rounded results for all inputs? And second, how efficient is RLibm? Because there are no bfloat16 math library available yet to compare to RLibm, we repurposed glibc and Intel's math library to a bfloat16 math library by converting a bfloat16 input to float or double, use either glibc or Intel's math library to produce the result, and then round the result back to bfloat16 value. We compared our RLibm's POSIT16 math library against the soft-posit math library, which is the only POSIT16 math library available. Our experiment shows that RLibm produces correctly rounded results for all available functions. RLibm provides 12 math library functions for bfloat16, and it produces the correctly rounded results for all inputs for all 12 functions. Comparatively, we found that when we repurposed glibc's float math library into bfloat16 math library, the 10 to the power of x function does not produce the correctly rounded result for one input. Similarly, Intel's float math library does not produce the correctly rounded result for the 10 to the power of x function for the same input. This case is especially interesting because the error results from the double rounding error. More specifically, when glibc and Intel's float math library computes the result of 10 to the power of x, internally they round the result to the float type. This float type result is correctly rounded result for float. However, when the float result is then rounded again down to bfloat16, it results in a wrong value. This example shows that we cannot easily repurpose an existing math library for one representation to create a correctly rounded math library for a different representation, even if the existing math library is a correctly rounded math library for that one representation. To guarantee correctly rounded results, we need to create a native math library for each representation. Additionally, we found that all 11 POSIT16 functions provided by RLibm produces the correctly rounded results for all inputs, and similarly, soft-posit math library produces the correctly rounded results for all inputs for the available functions. However, soft-posit math does not provide approximation functions for log10, e to the power of x, sin h, and cosine h. Lastly, RLibm provides log2 of x function for 32-bit float representation, which produces the correctly rounded result for all inputs. However, both glibc and Intel's float math library does not produce the correctly rounded result for all inputs. In fact, glibc produces wrong result for 14 million inputs. When we repurpose glibc and Intel's double math library for float, they produce the correctly rounded results for all inputs. Our experimental evaluation also shows that RLibm is efficient. The graph shows a speedup of RLibm's bfloat math library function against glibc's float math library in blue bar and glibc's double math library in orange bar. RLibm's functions for bfloat16 are on average 1.4x faster than glibc's float math library and 2x faster than glibc's double math library. The right graph shows a speedup of RLibm's bfloat16 math library functions against Intel's float math library in blue bar and Intel's double math library in orange bar. RLibm's functions for bfloat16 are on average 1.3x faster than Intel's float math library and 1.4x faster than Intel's double math library. For RLibm's math functions for POSIT16, the efficiency of the math functions are comparable to the math functions available in soft-posit math. The functions in soft-posit math are super optimized with integer operations without using floating point operations. Comparatively, RLibm uses floating point operations, but yet still produces comparable results. We're looking into ways to optimize RLibm with integer operations. Finally, RLibm's log2 of x function for 32-bit floating point is 1.3x faster than glibc's float and double math library, while it is 1.1x and 1.2x faster than Intel's float and double math library. Our log2 of x function for float type is faster than both glibc and Intel's math library, while producing correctly rounded results for all inputs. glibc's float math library produces wrong results for 14 million inputs, and Intel's float math library produces wrong results for 200 inputs. Our evaluation shows that using our approach in approximating the correctly rounded result, it is possible to create math libraries that are both efficient and correct. We're still actively creating correctly rounded approximation functions for other elementary functions and number representations. In conclusion, many exciting new representations for approximating real numbers have been proposed recently, and there is excitement in the machine learning and HPC domain to use these representations. However, these representations do not have native math libraries yet. So we present a novel approach in creating native math libraries for these representations that are efficient and produce correctly rounded results for all inputs. In contrast to prior work that focuses on generating approximation for the real value of f of x, we propose a radical approach that approximates the correctly rounded result instead. We also propose an approach to reduce the problem of generating polynomial approximations to a linear program problem. We show that using this approach, we can create math libraries that are not only correct, but also fast. In particular, our log2 of x function for the float type is faster than both glibc and Intel Math Library and produces correctly rounded results for all inputs. Thank you very much, and I would highly encourage you to try RLibm and the Math Library Generator, which are both publicly available. And if you have any questions or comments, please do not hesitate to contact us.